Welcome to our daily revision booster, which today is going to have a look at diseases, the reversible reactions, and redshift and the Big Bang. First things first, it's today's daily formula, which is for potential energy. So potential energy in joules is the mass in kilograms times the height in meters times gravitational field strength. Do obviously look out for those little tricks they put in sometimes to make sure the mass is in kilograms and the height is in meters. If they're not, remember to convert before you use this. Today's biology blast then, we're going to have a look at infections and diseases. So first up, we're going to have a look at some of the delightful human infections, so prepare yourselves some delightful pictures as always. The first infection we need to know about in humans is athlete's foot, which is caused by a parasitic fungi called dermatophytes. Now, they like to grow in these conditions that are nice and warm and humid, so between your toes is perfect for them. And what you'll find is that if you do have athlete's foot, then you're going to start to show symptoms like cracked, flaky skin, you'll have itchy skin there, so rather unpleasant as you can see from the pictures. The way that athlete's foot is spread is by either direct contact, so playing footsie with people with athlete's foot, not a good idea, or by indirect contact, by coming into contact with it on a surface. In terms of the treatment, then it's an antifungal cream that will then kill the fungal infection and your foot will return to normal. Our second infection is food poisoning, which is caused by a number of different bacteria creating toxins that then have those very clear effects of food poisoning. So three good examples of these bacteria: Campylobacter, which we'll find in raw meat, unpasteurized milk and untreated water; Salmonella in raw meat, eggs, raw unwashed vegetables and unpasteurized milk; and E. coli, which is in that raw and undercooked meat, unpasteurized milk and dairy products. In terms of the conditions under which these bacteria can survive then, the key thing to remember is that putting food with these bacteria on in the fridge or the freezer isn't going to kill them. The only way you can actually kill these bacteria is by thoroughly cooking the food. If you are unlucky enough to become infected with any of these food poisoning bacteria, then you can expect stomach pain, diarrhea, vomiting, simultaneously in many cases, a fever, and if it's a severe case that goes untreated, then it can actually result in death. So it can be quite a serious thing. In terms of how those bacteria spread then, it's all down to poor food hygiene. So not obviously washing your hands between touching raw meat and touching vegetables that aren't cooked, storing things badly in the fridge and so on. The way that we treat it is just through using fluids, so drinking plenty when you are suffering with it, because it will just rehydrate you at that point. Our third human infection are the STIs, sexually transmitted infections. Now, these are caused by a range of bacteria and viruses that are spread person to person through unprotected sex or genital contact. They can also be spread by bodily fluids or skin-on-skin contact. So this is where sharing needles or blood products being used can be another source of transmission. One of the big issues with these is that they're often asymptomatic initially. So that just means they don't show symptoms in those early stages, which means that the people who've got them don't necessarily know they do, and therefore that increases the risk of them spreading from one person to the next. In terms of how to avoid actually getting an STI, then you can either avoid sexual intercourse altogether, or if you are going to engage in sexual intercourse, then use a form of protection like condoms. So 4 STIs for us here then. First of all, chlamydia is a bacterial disease, and you'll get pain when urinating and a discharge from either the penis or vagina, depending on which one you've got. In terms of its treatment, it's a course of antibiotics. For gonorrhea, another bacterial disease, you get a burning pain when urinating and discharge from the vagina, and again treated with a course of antibiotics. For genital herpes, which is a viral infection, then you develop these painful blisters or sores. Unfortunately for these, there is no cure. So if you get genital herpes, then that's just the gift that keeps on giving throughout the rest of your life. Last one is HIV, which is another viral infection there. And what you're going to see in terms of the symptoms of HIV is a weakened immune system. And often that's going to result in AIDS in the long term. We don't have a cure for a HIV infection, and we can now use some drugs to control the actual symptoms by taking what's called antiretroviral drugs for life, but you can't cure it. You will always be HIV positive. If we take a little moment to think about HIV in a little bit more detail, then HIV stands for Human Immunodeficiency Virus. It's one of those tricky viruses that we're really struggling to get to grips with, because what it does is it actually invades the white blood cells and reproduces inside them. So whereas other infections are white blood cells are the bits actually attacking them, in this case the virus is inside those white blood cells reproducing. Now that means the white blood cells can't produce the antibodies to have their effect on them, because the virus is actually inside the white blood cell itself. As we destroy those white blood cells as the virus replicates, then what we find is our immune system becomes much weaker and the patient becomes more susceptible to those common infections that usually you'd be able to fight off without too much struggle. During the final stages of your HIV infection, then you are going to be diagnosed with what's called AIDS. And that's just where the body can no longer fight off those life-threatening infections. And a lot of people with HIV infections that have progressed onto AIDS will die of a secondary infection like pneumonia. One of the things they could ask you in terms of all of these communicable diseases, the ones that can spread from person to person, is how we can actually reduce the spread of them. And there's just a few really obvious things that you can write into an answer there. If we're talking about a disease that's spreading from person to person through obviously the droplet infection method through the air, then covering your mouth and nose when you're coughing and sneezing, not touching infected people and objects. If we're talking about a sexually transmitted infection, using protection there. If we're talking about something spread through bodily fluids, not sharing needles. If it's a food poisoning one, then obviously making sure food is cooked properly. And then just taking some obvious steps like don't poke wild animals because they carry a range of infections, so avoiding animal bites. Making sure you wash your hands before you eat and after you go to a toilet, etc. So anytime they ask you how can you reduce the spread of disease X, think about its method of transmission first of all, and then apply that bit of common sense as to how you could stop it. First reminder of today's daily formula then, potential energy in joules is the mass in kilograms times the height in meters times the gravitational field strength. For today's chemistry check, we're going to be having a look at the reversible reactions and equilibrium. So when we're talking about a reversible reaction, then what we're looking at is a reaction where the products can react together to form the original reactants. So that means that not only can it go forwards and the reactants form the products, but we can have a backwards reaction where the products can form the original reactants. And you can always see a reversible reaction because it has that kind of half forwards, half backwards arrow as the symbol. Just to give you an example of what we mean by forwards and backwards reaction, at the top we have the overall reversible reaction with its reversible reaction sign in the middle there. If we look at the forward reaction, it's the one that's going from left to right. So we start off with our hydrated copper sulfate and we're going to make copper sulfate and water. The backward reaction is the one that goes from right to left. So that would be copper sulfate plus water makes the hydrated copper sulfate. If we've got something called a closed system, then this is one in which a substance can neither enter nor leave. So this would be something like a conical flask with a stopper in the top. So nothing can enter, nothing can leave it. And if we've got a reversible reaction occurring within one of these closed systems, then it's going to reach an equilibrium. So that means that the rate of the forward reaction and the rate of the backward reaction are equal to one another. So this means that the concentrations of all of the reacting substances will also remain constant. What we do find though is that we usually refer to this as a dynamic equilibrium, because it's not a case of it's got to this point of them having equal amounts and it stops. The forward and backwards reactions are still occurring, but it's not changing the amounts of those substances because they're happening at the same rate. So dynamic because the forward and backwards reactions still happen, equilibrium because the rate at which they're happening is equal, and therefore the concentrations of all reacting substances remains constant. The last bit of our chemistry check today is for the higher tier folks only. So if you're not doing the higher tier, you can jump on to the physics section now. For those of you doing higher tier, you need to know about the equilibrium position. Now, when we're talking about the equilibrium position, it's a description of the relative amounts of the reactants and the products in that reaction mixture when it's at equilibrium. And what we find is that this is able to move. So the equilibrium position is on the left when the concentration of reactants is greater than the concentration of the products, and the equilibrium position will be on the right when the concentration of reactants is less than the concentration of the products. But when we change conditions, so if we change the temperature, the pressure, etc., then what we find is that equilibrium position can move. And this is something we're going to look at with the whole idea behind Le Chatelier's principle. What we're going to do then is take each of these conditions that could change in turn and have a look to see what it does to the equilibrium position. So first one is pressure. Quite simply, if we increase the pressure, then the equilibrium position moves in the direction of the fewest moles of gas. So this is where you look at your balance symbol equation and look at the state symbols. The only bit we're focusing on are the gases, so the ones with the G in brackets. In the example I've given you here, everything is a gas. So we can see on the left, we've got 2 moles of sulfur dioxide and 1 mole of oxygen. So 3 moles of gas on the left and 2 moles on the right. So because we've actually got 3 moles of gas on the left and 2 moles of gas on the right, if we increase the pressure at which this reaction is taking place under, then the equilibrium position moves to the right because that's towards the lower number of moles of gas. So increasing the pressure, the position moves in the direction of the fewest moles of gas. The second condition we could change is the concentration. And if we increase the concentration of a substance, then the equilibrium position moves in the direction away from the substance we've increased the concentration of. So again, we've got our example in the middle there. And if we were to increase the concentration of the hydrochloric acid, which is HCl on the left, then the equilibrium position moves to the right because it moves away from the direction of the substance we increased the concentration of. The third and final condition we need to consider is the temperature. So if we increase the temperature of our reaction, then the equilibrium position moves in the direction of the endothermic change. So for this one, what we need to do is have a look at the energy change in the reaction, which is shown by the delta H value. Hopefully we do remember that when we're talking about an exothermic reaction, it has a negative sign for the energy change, whereas an endothermic reaction would have a positive sign. So in this case that I've given you as the example, then the forward reaction is exothermic because it has a negative sign there, which means that if the forward reaction is exothermic, the backwards reaction is endothermic. So if we've increased the temperature of this reaction, then the equilibrium position moves to the left because that's the direction of the backwards reaction, the endothermic one. Quick reminder for you then of our 3 conditions and what the effect is on the equilibrium position. If we increase the pressure, it goes towards the fewest moles of gas. If we increase the concentration, it moves away from the substance with that increased concentration. And if we increase the temperature, it moves in the direction of the endothermic reaction, so the delta H plus value. Quick reminder of today's daily formula, which is potential energy in joules is the mass in kilograms times the height in meters times the gravitational field strength. Today's physics prep then is all just for the GCSE physics folks, and we're going to have a look at the Big Bang Theory. Now, hopefully we do remember that if we look at how ideas about the universe have changed over the many years that humans have been around, then it's always changed as a result of observations being made. And from those observations, we've then had a little bit of creative thinking occurring to try to explain the observations. And that's how we've come up with these different ideas about the universe over time. So the most widely accepted model for our universe today is the Big Bang model. Now, what we actually have with our Big Bang theory is that the universe actually started as something very dense and very tiny that then underwent this sudden expansion about 13.7 billion years ago. And what we can actually see from this is that the space between the galaxies is expanding, and we on planet Earth are not at the centre of the universe, contrary to what some people may act as if they believe. The reason that the Big Bang theory is widely accepted today is because we've got two key pieces of evidence for it. We've got cosmic microwave background radiation, or CMBR, and we've got redshift. If we consider the cosmic microwave background radiation, or CMBR, first of all, then this was actually something discovered back in the 1960s. And what we found was that no matter where we aimed our instruments within the sky, then there was this microwave radiation being detected. And what scientists worked out is that this was left over from the Big Bang. So what we've actually found is that over the many years since the Big Bang occurred, then the very high energy, high frequency radiation has actually been stretched until it's in the microwave region of the electromagnetic spectrum today. And what we expect to happen is that as time goes on even further, then it will continue to be stretched and move further into the radio wave end of the actual electromagnetic spectrum. But today we're in the microwave region because we've actually stretched that radiation over the 13 billion odd years that we've had it actually in existence. The second key piece of evidence we need to know about is the work of Edwin Hubble back in 1929. What Edwin Hubble actually did was he measured the speed of galaxies from the absorption spectrum of the light that they emitted. So hopefully we know that the visible spectrum involves wavelengths of light of red, orange, yellow, green, blue, indigo and violet, as you can see in the picture in the middle there. And when a light source is moving away from you, then the wavelength of the light that it emits will increase and the frequency will decrease, because where we increase the wavelength, then the frequency will decrease. And this is the principle of redshift. So what we're actually seeing is that these galaxies that Hubble was looking at were moving away from us, so that the light that they were emitting was actually being moved to the red end of the spectrum. And you can see there that the wavelength of the red light is in the 700 nanometer wavelength, so it's longer. Whereas if we had a light source that was moving towards us, then it would be moved to the blue end of the spectrum, because what we'd see there is the wavelength would be decreasing and the frequency increasing. Now, because all of the galaxies that we looked at were demonstrating this redshift, that told us that they were moving away from us, because the wavelength of the light was being increased and therefore the shift to the red end of the spectrum. And if we've got a source that's moving faster, we just get a bigger redshift. So from the work that Hubble actually did, he actually used redshift to work out that all of these galaxies that he was observing were moving away from us. And he also noticed that the more distant the galaxy was to us, then the faster it was moving away. So this gives us that idea that we had our universe starting at this central point, but it's still expanding to this day. And all of those galaxies that make up our universe are actually moving away from us and moving away from each other to this day. Hopefully at the end of this daily booster, you can now recall different human infections and how we can prevent the spread. You can recall what a reversible reaction is, the symbol for it, and also explain equilibrium position if you're doing the higher tier. And for those of you doing GCSE physics, you can also explain the Big Bang theory and the evidence for it. Don't forget to join us again tomorrow for our next daily booster.